Hello everyone, welcome again to Discrete Mathematics and its applications with me Adila Krishnadi. We are now at the seventh part of the topic relation, and in this part we will discuss partial orderings. Partial ordering is another property of binary relation like equivalence relation, but we define this differently. Given a set A and a binary relation R on A, we say that R is a partial order or non-strict partial order if and only if R is reflexive, antisymmetric, and transitive. So the property to be satisfied by R are reflexivity, antisymmetry, and transitivity. Remember, in equivalence relation, R has to be reflexive, symmetric, and transitive. Here, in partial order, R has to be reflexive, antisymmetric, and transitive. We use this notation with curly less than or equal sign to denote a partial order. Now, if R is a partial order on a set A, then the pair A comma R, so the set and the relation together, is called a partially ordered set or poset. And elements of A are exactly elements of the poset. So when we consider a set together with a partial order on that set, then we have a poset. And for two elements of A and B, small a and small b, then we write A is less than or equal to B with subscript R whenever A comma B is in R, and also A is less than B if A is less than or equal to B and A is not equal to B. So here the notation less than or equal here applies generally to every partial order R, so it doesn't have to be the usual less than or equal sign. The subscript R is omitted if it's clear from the context, and instead of R we sometimes use the pair A comma less than or equal sign to denote a poset. Now let's see some examples. Here's the first one. So you have a set A 1 2 3 containing integers 1 2 3 4 and 5, and a set and the relation R given there. So is this a poset? Well, to answer this, we check whether this is reflexive, antisymmetric, and transitive. Because this is a finite set, it might be easier to simply draw the graph representation. So let's start with 1, and then 2, and then 3, and then 4, and then 5. So you have a 1, 1, 2, 2, 3, 3, and 4, 4, and 5, 5. So it's clear that it's reflexive. And then you have 1 to 3, 1, 3. You have 1, 5, and then you have 4, 2, and then you have 5, 3. Now if you look at this diagram, this graph, it is clear that the relation is actually transitive because all the two hops have shortcuts, and it is also antisymmetric because in addition to having loops, there is no edges running, a pair of edges running in the opposite direction involving the same two elements. So it's a yes. Hence A comma R is a poset. Now let's see another example. Now this time we have an infinite set Z, which is a set of integers, and the standard less than or equal relation. Is this a poset? Let's see, is this reflexive? So we check reflexivity. So let a be an integer, then obviously a is less than or equal to a, right? So yes, a comma a is an element of the relation. Yeah, so it's yes. Is it antisymmetric? So suppose let a and b be integers with a less than or equal to b and b less than or equal to a. Then obviously, because they are integers, a must be b, which gives us antisymmetry, right? And for transitivity, so suppose let a, b, and c be integers with a is less than b and a is b is less than or equal to c. Then of course, by this too, this implies that a must be less than or equal to c, right? Because they are all integers. So uh, a comma c is in also in the relation less than or equal to. So it's a yes, it's a transitivity, and therefore c comma less than or equal is a poset, right? Now so we have two examples. Let's see another example. This time we look at the relation, the set of natural numbers n and the relation less than. And is this a poset? Well, we could simply check whether any of the three properties in the definition of n poset are violated. So let's check. So is it reflexive? The answer is no, right? Because if a is a natural numbers, then the relation a less than a is impossible. Yeah, so a comma a is not in the relation less than for every a. Yeah, for, well, at least one a, right? And because natural numbers are not, set of natural numbers are not empty, so therefore it's a no, and therefore this pair is not a poset. So that's three examples. So we see another example. Now this time we check whether this is a poset, and again we check reflexivity. uh, Let a be an integer. Obviously a is less than or equal, absolute value of a less than or equal to absolute value of a, so this is absolute value. So a comma b is in the relation if absolute value of a is less than or equal to absolute value of b. And since a absolute value of a is less than or equal to absolute value of a, then we have that a comma a is in the relation, so it's a yes. Now how about antisymmetry? So take integers a and b with both a comma b in R and b comma a also is in R. Then what does it mean? It means that, well, absolute value of a must be absolute value of b less than or equal to absolute value of b, and absolute value of b is less than or equal to absolute value of a. Yeah, since absolute value of a and absolute value of b are all in set of natural numbers, we have that absolute value of a is absolute value of b equal to absolute value of b, right? Let me just Fix this first. Absolute value of A is equal to absolute value of B. Yeah, these two, right? Now, does this hold? For every uh, integers A and B? The answer is no, right? So take A to be say 1 and B to be -1. We see that A, absolute value of A is actually less than or equal to absolute value of B, and absolute value of B is less than or equal to absolute value of A. Yeah, or in other words, 1 comma -1 and -1 comma 1 are in the relation. Yeah, but clearly 1 is not equal to -1, so not antisymmetric. Yeah, because of this, the pair Z comma R is not a poset. So we've seen two examples of posets and two examples of pair of set and relation that is not a poset. They are not a poset. So so now we look at three exercise questions. So you're given a pair, a set, and a binary relation on that set, and determine whether these pairs are posets or not. So have a look at these questions and try answering them uh, before we discuss the solution in the next videos.